Typically, writing a PhD or master's thesis is just the first step in a scientist's career, but there are some rare cases where a student hits the ball out of the park on their very first try. Across history, there are several cases of a student's thesis having a huge impact on not just their scientific field, but even the world as we know it. Several scientists have even gone on to win Nobel Prizes for contributions made while they were a student. I tracked down 8 outstanding theses stretching back to the early 1900s, and in this video I will show you what made them so special. Their topics span physics, mathematics, chemistry, astronomy, computer science, and biology. Each distills the work done by a student over the course of their degree. For a master's, this is typically a couple of years, and for a PhD, it could be from 3 to more than 6 years. The thesis is a document that collects all the students' findings and will be evaluated by a panel of experts. Yet while these theses are shining examples of what young scientists can do, they don't quite show the whole picture. For every student whose work wins a Nobel Prize, there is a mix of skill, determination, supervisor's input, and luck. To be successful, you don't have to write an award-winning thesis, and I found a couple of cases of outstanding scientists who never wrote a thesis at all. I'll include those at the end of the video, but first, let's see what we can learn from the best theses of all time.
John Nash.
And the Oscar goes to...
I just thought, that sounds neat.
And in the atom there's a central core.
Had a tremendous impact on my life.
You were overlooked for the Nobel Prize. How did that feel at the time?
It's quite different to get official recognition.
This first PhD thesis, also called a dissertation, was handwritten by Paul Dirac and simply titled Quantum Mechanics. He submitted it at Cambridge in May 1926. While some pages contain beautiful handwriting, seemingly written in pen, others contain scratch math written out and often crossed out in pencil. In one corner of a page, a seemingly unrelated drawing of a candlestick appears. Dirac's thesis was the first to be written on the subject of quantum mechanics, which had only been introduced by Heisenberg a year earlier. At the time, Dirac was only 24 years old. Dirac writes in his preface that the following dissertation is a development of this theory from a slightly different point from that of Heisenberg's paper. The table of contents shows that the thesis covers ideas such as algebraic axioms, motion of a particle in a central field, frequencies of the hydrogen spectrum, systems with more than 2 electrons, quantum time, theory of Compton scattering, and intensity of scattered radiation. These are all key ideas that you would still expect to see in any quantum mechanics textbook today. Throughout his thesis, Dirac lays the groundwork for a new mathematical approach to quantum mechanics. The pages aren't laid out particularly linearly, and honestly, it's hard to read this thesis, but you can skim through it. Here it looks like he might be developing the Dirac delta functions that came to be named after him, and I think we get his thoughts towards what would go on to be known as the Dirac equation, something that is now considered one of the most important equations in quantum mechanics. The Dirac equation merges quantum mechanics with special relativity, describing particles moving at close to the speed of light. Thinking about these ideas helped lead to discoveries including the positron, and in 1933 Dirac was awarded the Nobel Prize in Physics, along with Erwin Schrödinger, for his contribution to the discovery of new productive forms of atomic theory. This next thesis has been called the most brilliant PhD thesis ever written in astronomy. It is titled Stellar Atmospheres, a contribution to the observational study of high temperature in the reversing layers of stars. It was written by Cecilia Payne. It was her PhD thesis at the Harvard College Observatory, submitted in 1925, and it changed not just how we study the stars, but what we know about their composition. In particular, she proved that absorption lines, the dark lines left behind when observing a star's light, differ between stars not just because of their elemental makeups, but because of their different temperatures. She found that higher temperature made it more likely for atoms in the stars to become ionized, which changed their absorption spectra. Yet despite the importance of these discoveries, Cecilia Payne-Gaposchkin, as she was known after marriage, wrote a thesis full of caveats from the very beginning, perhaps because, as she writes, astrophysics is a young science, or perhaps because she herself was a young student. The editor's note before her dissertation reminds readers, it should be remembered that the interpretation of stellar spectra from the standpoint of thermal ionization is new, and the methods employed here are as yet relatively primitive. Hence, we must expect that a study such as is presented here will promptly need revision and extension in many places. Yikes! These unwarranted doubts about Payne-Gaposchkin's work also nearly resulted in the omission of one of the paper's biggest discoveries. During her work on spectra, she made the discovery that our Sun was made nearly entirely of helium and hydrogen atoms. However, senior colleagues warned her that this result was clearly impossible. To save face, Payne-Gaposchkin included the result in a chapter titled The Relative Abundance of Elements, but with a note on page 188 that the finding is almost certainly not real. Luckily for Payne-Gaposchkin, history was on her side. The Sun is indeed made nearly entirely of hydrogen and helium, and it would have been tragic if she had removed that finding just because other people found it hard to believe. Another scientist who also made an unexpected discovery whilst collecting data for their astronomy thesis was Jocelyn Burnell. And like Payne-Gaposchkin, Burnell's findings were also initially dismissed by her more senior colleagues. In her 1968 PhD thesis for Cambridge University titled The Measurement of Radio Source Diameters Using a Diffraction Method, Burnell was consumed by collecting data signals of rare astronomical phenomena called quasars. These signals are the bright lights emitted by matter as it heats up while spiraling into the center of a supermassive black hole. Burnell helped to build the radio telescope that she was using, called the Interplanetary Scintillation Array. Throughout the course of her observations, Burnell and her telescope generated miles of data, which she searched through with a fine-tooth comb to find more than 200 quasars in just a few years. Some nights she would review as much as 29 meters of data. Then one night she found a signal that didn't match up.
It wasn't exactly a twinkling radio source, and it wasn't exactly interference either.
Burnell had spotted a 1.3 second blip of high-frequency radio waves that didn't match quasar behavior. At first, her advisor Anthony Hewish thought it must have been an error in how Burnell had set up the telescope.
I didn't talk about it to my supervisor until I was pretty sure I knew what I was talking about.
Ultimately, Hewish and Burnell published her findings in Nature the same year that Burnell published her own PhD thesis on quasars. This discovery of pulsating radio stars, or more commonly now called pulsars, would go on to win Hewish a Nobel Prize in 1974, but notably not Burnell. Despite having identified the radio signal, Burnell was controversially overlooked by the Nobel Committee. As a young student, Burnell was not given credit for the discovery. The Nobel Prize was shared by Hewish and another astronomer named Martin Ryle, even though Burnell was the one who noticed the signal and argued that it was real. She later said that the fact that I was a graduate student and a woman together demoted my standing in terms of receiving a Nobel Prize. While she might have been snubbed for the Nobel, Burnell did go on to have a great career in astronomy and has since won other awards, including the Special Breakthrough Prize in Fundamental Physics in 2018 for her contribution to the discovery of pulsars. The prize money was roughly 3 times that of a Nobel, and Burnell donated all of it to the Institute of Physics to fund women and underrepresented ethnic minorities and refugee students to become physics researchers. There have been a lot of breakthroughs in computer science, and this next thesis is one of them, but you wouldn't expect it to have come from 1936. More than a decade before we even had the slightest semblance of computing with things like the ENIAC, a 21-year-old master's student laid the groundwork for digital computing logic. That student was Claude Shannon. Titled A Symbolic Analysis of Relay and Switching Circuits, Shannon's master's thesis explored how to apply Boolean algebra to electric circuits in order to control their behavior. This is the kind of logic that would later communicate binary instructions to computer bits like on, off, and if. Today, these simple instructions are still the backbone of all the complex computing at our fingertips. But this kind of usage was far beyond Shannon in the 1930s. Instead, he writes in his dissertation that this logic can be applied to automatic telephone exchanges, industrial motor control equipment, and in almost any circuits designed to perform complex operations automatically. Shannon's work was not in a field that is eligible to receive a Nobel, but he is commonly known as the father of the information age, and his thesis has been called the most important master's thesis of all time. After the master's, Shannon went on to do a PhD in mathematics, writing a thesis focusing on genetics in 1940. That thesis, unlike his first, didn't make much of a splash. It was titled An Algebra for Theoretical Genetics, and whilst it apparently contained some important results, Shannon lost interest in it. He later worked on cryptography, information theory, and early artificial intelligence. This next thesis is very unique. Some students complete their postgrad degrees by writing 100-page tomes to explain the work they spent years completing. Mathematician John Nash took a different approach. In 1950, Nash wrote a thesis for his Princeton PhD titled Non-Cooperative Games, and it was only 27 pages long. It included only 2 citations. While short and sweet, this thesis laid the groundwork for a mathematical concept now called Nash equilibrium that became part of the foundations of game theory. In his thesis, Nash explains that in finite games with multiple players, for example a game of poker, there must exist at least one equilibrium point at which each player has chosen their optimal strategy and would not be swayed by learning another player's plans. Beyond the poker example used in Nash's thesis, Nash equilibrium has a number of applications today, including helping robots navigate crowds and analyzing wartime strategies. And if you haven't heard of Nash equilibrium, maybe you've heard about the film based on Nash's life, A Beautiful Mind. The film won Best Picture at the 2002 Oscars for its portrayal of Nash's work on top-secret military code breaking during the 50s and 60s. For the work on game theory that he laid the foundations of in his thesis, Nash shared the 1994 Nobel Prize in Economics, so his thesis wasn't just notable for being short, it was also hugely impactful, probably the most impactful thesis per page of all time. In 2015, for his lifelong contributions to mathematics, Nash was awarded the prestigious Abel Prize offered by the King of Norway. Tragically, on his way home to New Jersey after receiving the award, Nash and his wife Alicia were killed when the taxi they were riding in crashed. Nash was aged 86. His legacy extends far beyond mathematics and economics. He also raised awareness of mental illness, having lived much of his life with schizophrenia. This next thesis is one that I've covered on my channel before. It is the work of Marie Skłodowska-Curie. Known simply as Marie Curie, she is famous for her work on radioactivity, but most people don't realize this pioneering work was part of her PhD thesis. Curie was a Polish-born scientist who moved to Paris to pursue her studies at the end of the 19th century. In Paris, she earned degrees in physics and maths, met her husband Pierre, and embarked on a PhD. As Curie herself says in her 1903 thesis for the University of Paris, her work was the extraction of new radioactive substances and the further study of their properties. The title of her thesis was Research on Radioactive Substances. This work was undertaken in the last few years of the 1800s, and by the time Curie's thesis was published in 1903, Marie, Pierre, and their colleague Henri Becquerel received the Nobel Prize in Chemistry for their work on radiation phenomena. In particular, the work laid out in Curie's thesis details the discovery of 2 new radioactive substances, polonium, named for Curie's native Poland, and radium. Both of these elements were many more times radioactive than uranium, discovered by Becquerel several years earlier. The original thesis itself remains radioactive to this day. Uncovering these new elements was physically tiring, made more difficult by the then, unbeknownst to them, radiation sickness that both Marie and Pierre suffered from. To find a sample of radium, the Curies sourced large amounts of a radioactive ore called pitchblende, and then ground, dissolved, filtered, precipitated, collected, redissolved, crystallized, and recrystallized the ore's elemental components until they had isolated a sample of radium chloride. Marie Skłodowska-Curie was the first woman in France to receive a PhD in physics, but for her it was only the start of a life of trailblazing work. She went on to win a second Nobel Prize, that one in chemistry, and she remained at the forefront of the most exciting physics discoveries of her time. When Carol Greider made a discovery in 1985 that would ultimately go on to win her the Nobel Prize in Medicine in 2009, she was only 23 years old and had not yet completed her PhD at the University of California, Berkeley. But let's back up. In 1984, Greider arrived at the lab of Elizabeth Blackburn, one of her future co-awardees, who was conducting work on telomeres. These are regions of repetitive DNA that protects a chromosome from damage. The shorter a telomere becomes as part of natural aging, the more easily a chromosome can be damaged until it can no longer replicate. As part of her graduate work in Blackburn's lab, Greider was looking for the key to telomere elongation when she found it in the form of an enzyme called telomere terminal transferase. It was over drinks with colleagues that this name was ultimately shortened to the catchier telomerase. This enzyme would have major implications for the study of aging and cancer. This discovery of telomerase was first published in the journal Cell in 1985, and Greider published her PhD thesis titled Identification and Characterization of Telomere Terminal Transferase in 1987. Nearly 20 years later, Greider, Blackburn, and their colleague Jack Szostak received a Nobel Prize for their work on this topic. When Donna Strickland got into physics, she was looking for something cool to study, and that's when she discovered high-powered lasers. As a graduate student at the University of Rochester, Strickland worked in the lab of Gerard Morel, who was trying to create high-powered laser pulses that wouldn't destroy the laser in the process.
And I just thought, that sounds neat. I'm going to go there and do that.
Strickland and other self-described laser jocks in the lab took this ambition and ran with it. As Morel had originally hypothesized, Strickland was able to create these powerful laser pulses through a mix of stretching the lasers to reduce their peak power, amplifying, and then ultimately compressing them back down, all without destroying the laser itself. Strickland described this process, called chirped pulse amplification, in her 1988 PhD thesis titled Development of an Ultra-Bright Laser and an Application to Multi-Photon Ionization. This laser amplification approach plays a major role in areas like medicine, where it's used in corrective eye surgery and medical imaging, as well as industrial machining. In 2018, Strickland and Morel won the Nobel Prize in Physics for their work developing this method. Now, while a number of incredible scientists have made a huge impact on their fields at an early age, this is far from the status quo. Most scientists will never win a Nobel Prize, and it remains very rare for a student's work to win. So what do these hugely impactful theses have in common? All of them were working on the right thing at the right time. There is an element of timing in all of these examples. The obvious part is that to be the first to discover something big, you need to be working on the problem at a time early enough for no one else to have made the same breakthrough, but late enough that the technology exists for you to make the discovery with. You need to come at the perfect time to build upon all of the existing knowledge that's already been laid down. Paul Dirac was brilliant and a great physicist, but also happened to be writing his thesis on a brand new topic just a year after Heisenberg and Schrödinger had totally changed the game with quantum mechanics. There were many open questions ready for Dirac to swoop in and solve in 1926. Without him, maybe someone else would have done the same, or maybe the whole field would now be done differently. Then there's the fact that these people all took a risk on ideas that might not have resulted in any breakthroughs. For every Marie Curie who spent years doing hard work to isolate radioactive substances, there will have been other people just as talented who didn't find what they were looking for. There are parts of experimental work especially that will always be outside of your control. There's an element of survivorship bias in these examples. They show off times when the hard work pays off big time, but many students out there are just as smart and work just as hard without the same results. The cases of Jocelyn, Burnell and Cecilia Payne shows some of the human factors to also consider. Students face the additional challenge of proving themselves worthy in the face of senior scientists who may not make it easy for them to do so. That's one reason why choosing the right supervisor is just as important as choosing the right topic to work on. But you also have to wonder, who does a list like this actually exclude? PhD and master's theses are a tradition that took shape in Eastern Europe, and so while the idea has spread pretty globally now, they aren't as influential elsewhere as they may seem in the Western world. Take India, for example. In the 1920s, PhD degrees were only still just being introduced in a handful of universities. Prior to this, education was assessed in other ways, such as through debates and oral presentations. Many Indian scientists have made significant contributions to science, including winning Nobel Prizes, without ever officially receiving a PhD. This includes C.V. Raman, who won the Nobel Prize in Physics in 1930 for his research on light scattering. He didn't have a PhD, and neither did Satyendra Nath Bose, who worked on quantum mechanics. Bose's name has been immortalized with Einstein-Bose condensates, named partially after him. Doctoral degrees were introduced even later in China, so some of their best scientists are also excluded from a list like this. Take, for example, Tu Youyou. With only the equivalent of a bachelor's degree in pharmacology from Beijing Medical College, Tu Youyou received the Nobel Prize in Medicine in 2015 for her work discovering a novel therapy for malaria in the 1970s. Notably, this treatment was found by studying ancient Chinese medical texts to see how malaria had been dealt with in the past. Looking through many ancient medical texts, Tu found a reference from 400 AD to sweet wormwood being used as a treatment for intermittent fevers, a prominent symptom of malaria. Tu isolated a compound found in wormwood that seemed to explain its anti-malaria properties and tested the solution first on mice and monkeys and then on herself and others in her research group before administering the treatment to malaria patients with an incredible recovery rate. It is the distillation of this compound's active ingredient, artemisinin, that won Tu the Nobel Prize for her contribution to malaria therapies that have saved millions of people's lives worldwide. To that point, many of these theses on my list won Nobel Prizes, but winning such a prize is still only one way to measure the impact of science. Some theses may be more impactful in other ways, such as influencing policy, raising awareness, inspiring people, launching a new field of study, or just being in a topic not recognized by the Nobel Prizes, such as pure math. At the end of the day, being a research scientist is about trial and error, learning the scientific process, and developing professionally. Science is hard work, but occasionally all the stars align for a student to change the course of history. Thank you to my Patreon supporters for making this video possible, and a special shout out to today's Patron Cat of the Day, Onyx.